is a new camera angle which I'm trying. I don't like this. This hand comes in way and go to old angle. Let's do that here. Let's see what's this. No, no. Okay. I'll go back to old. Okay. And before I go to background, I decided that I'll just read this paragraph and go to related one so that I'll get some context. Then go back to continue on this. Okay. So background settings. Now the until that reducing the number of bits of a model is directly related to inference latency for LLMs. But I think it makes sense for sorry, but I think it makes sense for me because I feel that it process all the bits, go through all the parameters. So if it's less, it's faster, right? I mean, parameters are not increasing, the number of bits is reducing. So maybe when you're reducing the number of bits, you're sharing the parameters. Now it doesn't make sense. Let's see. The following section gives the background to understand this relationship. Afterward, we provide a background on quantization data types and methods. Okay, let's see what do they say. Relative work. Relative work. Large language model quantization. The most closely related work is on large language model quantization for models more than a billion parameters. Okay. Compared to the smaller models, LLM quantization faces some unique challenges such as emergent outliers and optimized low bit inference for LLMs. I see delimiter a lot, and delimiter dead is one of the other thing. So maybe that's someone who works on quantization a lot. Yeah, maybe. A major defining factor between approaches is zero-shot quantization methods uh, that directly quantizing model without any additional information, and one-shot quantization methods need a mini batch of data for quantization. Let's take two types of quantization methods. Maybe one-shot quantization methods, as I was saying, need a mini batch of data that gives you the idea of outliers or type of outliers that's there. Maybe, maybe the case. And with that,
Yep. While one-shot methods are more accurate, such as GPTQ, which optimizes the rounding during quantization via mini batch of data, they are also more complex and may require hours of optimization before a model can be used. On the other hand, the advantage of zero-shot methods is that they can be used immediately, which makes them easy to use. But zero-shot quantization methods often fail at lower precisions, which we are trying to, which we are hovering around. Quantization methods. Another aspect related to our work are quantization methods, which can be grouped into specific categories. For example, there are methods associated with blocking and grouping, centering, land data types that are found through clustering, Under codebook optimization. While our work studies grouping and blocking, we only study one data type that groups similar weights through their quantiles of the entire input tensor. I think we'll cover this grouping blocking in the next parts that we're going to cover. While we do not study learn data types in depth, we are the first work that shows that these are crucial for improving bit level scalings for LLMs. Hmm. Scaling laws for inference. This is what we are interested in. Early work in scaling laws highlighted the importance of studying how variables change with scale, since scale is one of the best predictors of model performance. Particularly for inference, there's been a lot of there's been work that studies scaling trends of zero shot performance for 4 bits versus 16 bits. Was That's what they're doing? No, 4 and 16. Okay. We study precisions from 3 to 16 and disentangle the factors that improve scaling. Okay, they're trying to see what factors are improving the scaling. Work by Okapop et al. Looks at scaling inference in a production setting where large batch sizes are common, while they only study quantization rudimentary. The disentangle factors that lead to better model flops neutralization, since reducing the bit precision of bit bits loaded leads to higher MFU. It is similar to our approach to studying bit level scaling. The main difference is that we vary the bit width of models and study small batch sizes that are common for consumers. Scaling laws. The paper in general is trying to tangle the factors for scaling improvements, trying by trying 3-bit through 16-bit precision. Okay, first of all, what's the relationship between inference latency and total model bits? What do I think? The number of total model bits. Okay, let's not think. Okay, let's think. If total model bits is proportional to number of parameters, the number of operations you do reduces at each level and everything. So the latency is less. Well, the main goal of our work is to find the best trade-offs between modal bits and zero-shot accuracy for LLMs. And finding the trade-offs. Let's see if that's- the total model bits are strongly related to inference latencies. The overall computation latency is The time it takes from start to finish of a computation is mainly determined by two factors. How long does it take to load the data from the main memory into caches and registers? And second, how long does it take to perform the computation? For example, for modern hardware like GPUs, it usually takes more than 100 times longer to load a number than to do a arithmetic operation with that number. I'm so sorry with that number. Therefore, reducing the time spent loading the data from the main memory is often the best way to accelerate overall computation latency. Such reductions can be achieved mainly through caching and lower precision numbers. Caching can be reduced Caching can reduce the overall latency of matrix multiplication by a factor of 10x or more. Given that neither matrix entirely fits into the element cache of the device, matrix multiplication BW H with the batch B and the parameter matrix W, we load each row of B and each column of W and then multiply them. Thus, multiple loads from global memory occur for each row or column which can be cached. If B entirely fits into element cache, no reuse is possible because neither W or B is loaded more than once from global memory. This occurs if the inference batch size is below 60 or 200 for an RTX 3090 or RTX 4090 GPU. As such, caching is ineffective below these batch sizes. The inference latency is solely determined by the memory loaded from W, the weight matrix. Thus, in the case where mini batch fits into L1 cache, inference latency can be reduced by using a smaller model with smaller W or by compressing an existing model to a lower precision parameter in W. Using a smaller model. For example, beyond the arithmetic invocation of improved rounding for quantization beyond their algorithmic innovation of improved rounding for quantization, Frontier et al. Also developed inference CUDA kernels for 16-bit inputs and 3-bit integer weights, which yields inference latency improvements of up to 4.46 times compared to 16-bit inputs and weights for OPT, which is 175 billion, close to 5.33 times reduction in the model bits. Oh, as such, reduction in the total model bits is strongly correlated with the inference latency for small inference batch sizes. We provide additional data from a roofline model and preliminary data from an optimized implementation in Appendix E. Okay, the paper also explains the relationship between the inference latency and total model bits beautifully, as it is they say the, as it takes a lot of time. What is an hour for a lot? About numbers. increase in time to load the data to GPUs compared to the time taken time it takes to operate on the data. So the main focus in many optimizations is to reduce this data load latency, implying some sort of cache. We can make uh, as much data as we can cacheable by either reducing the model size or using quantization and reducing number of bits it takes per parameter. Thus, what do we learn from this? Thus, it states the importance of bit precision in improving importance and relation of bit precision to improving the inference latency. When we talk about data types, we use four different data types. For integer and float data types, we use they use IEEE standards. Or float data type has a exponent base, okay, number of exponent bits. Now we also use quantile quantization, a lossy maximum entropy quantization data type where each quantization bin holds an equal number of values. This ensure that each bit pattern occurs equally often. Finally, we use dynamic exponents quantization, which uses an indicator bit to separate an exponent bit region and a linear quantization region. I don't understand this. Hello. Exponent uh, can vary from value to value by shifting the indicator bit. Okay, what is blocking and grouping?